Okay, so welcome back to this next video in which we are calculating conditional expectation. Right, so we have this setup where we have a random variable x, which is mapping an abstract probability space onto the real line, and we've already discussed that x is going to be normally distributed. So normally distributed means 0, variance 1. And we've created this other random variable y, which is we defined by taking a function of what the random variable x maps you onto. So we took the value that x maps you onto, and we basically just squared it. So y is going to map any outcome s onto the value that x maps s onto, but that value squared, basically. So that's the equation that tells us what to do with any outcome under the function y. Right, so if we want to take the expected value of the random variable y given x, so what does that mean? Let's think about what this means. This means restrict your attention now down to the probability space, which is that x is equal to some value little x. So basically, in fact, I'm going to use a different symbol. I'll use a. So basically what this means is it means x, we now know what the value is. So x could have been any real number, but we know what its value is. So it's now fixed. So let's just say a is an element of the real numbers. So a is some value that x could take. We are now saying that we have fixed that value. So here is that value. And we are then saying, now, restrict your attention completely down to that probability space. So in here, there is a as an outcome. And basically now what you are doing is you are saying, I don't care about the rest of this probability space. I'm only interested in that set containing a. That has now happened. I'm going to promote that up to being my entire probability space now. Now, a will have a certain set in this original abstract probability space that corresponded to it. So there will be a bunch of outcomes, potentially more than one, but this is the set of all outcomes which were mapped onto a by this random variable x. So I will just denote that x inverse of a. So that just means, it doesn't mean the inverse, I shouldn't have called it the inverse. By that symbol there, I mean the pre-image of a. So, strictly speaking, what I mean is all outcomes in this abstract probability space which are mapped onto A. It's a little bit of abusive notation because that does probably mean inverse, but the inverse might not exist because this might not be a one-to-one function. So there might be multiple things that are all being mapped onto A, and then the inverse of A doesn't exist because which one do you map it onto? Instead, the pre-image exists, which is this set of all things which are mapped onto A. Now, the inverse might exist. You know, there might only be one thing that was mapped onto A, but it's not necessary. Right. Okay, so there's some set back in the abstract probability space here, which is all of the points in this abstract probability space which are mapped onto A. So basically now what we are doing is we are saying this has happened, one of these has happened anyway. So we're now saying we restrict our attention down to this probability space, which is the equivalent of this probability space over here. And what we now want to know is if we look at the random variable y on this probability space, well, what's its expected value? So basically, we're doing away with all of this rubbish, all the rest of this probability space over here. We're doing away with it. We're getting rid of that. I don't care about it anymore. We are conditioning on x being a certain value a, and you'll notice how we are keeping this completely general. I have not told you what the value a is. It could be any value, so these arguments work perfectly well for any value of a. Right, so now we're restricting our attention down to this probability space. So if I pull this probability space out and draw it down here, so we've taken it away from the rest of that clutter back up there. And here it is. This is our entire probability space now. So this is all the outcomes that were mapped onto x is equal to a by the random variable x. So this is the pre-image of a, effectively. Right, and we know that the random variable x is going to map all of these points onto the probability space, which just contains the element a. So it's going to map them all onto there. Now what we want to do is look at the random variable y. Well, this is very, very simple. What does the random variable y map you onto? Well, it maps you onto the value of x squared, so there's only one value it can map you onto. So it has to map you onto a squared. So now the random variable y, restricted to this probability space here, this new probability space that we're conditioning on, is just a constant. Right, so what's the expected value of a random variable which is just a constant? Well, it's just that constant. So the expected value of this random variable y, given that we are conditioning on this probability space, which is that x is equal to a, is equal to a squared. Okay, so that gives us the value for this specific case. But we might now want to view this conditional expectation as being a random variable in its own right. Now, what do I mean by that? I mean that we could set this up as a random variable. We could set it up as another, where shall I put this? The picture's kind of getting cluttered. Where shall I put it? We'll put it down here. I could set up another random variable from this probability space, which I could call the expected value of y given x. Okay, and what basically it does is it will look at your value of x and it will say, if that value of x has happened, what's the expected value of y given that that value of x has happened? So basically, from this probability space, what it will do is it will take any outcome, it will look at what the value of x is, it will look at what value x maps you onto, and it will say, now, okay, that value of x has happened, whatever your value of x is. So basically, it will insert in, for a, it will insert in the value of x that is ascribed to that outcome s, and basically, it will then map you onto this value here. So if I insert in x of s for a squared, it will map you onto x of s squared. So, in fact, this random variable is going to be exactly the same as our y random variable, which is kind of trivial in this case. What's kind of trivial about this example? So basically, this is a random variable though, and it's a useful random variable, and we're going to see why using this notation, you thinking of conditional expectation as a random variable is so powerful. But again, it's going to map you onto the positive real numbers here. Well, the non-negative real numbers. Right, so I just want to review once again what that means, what it means to think of this as a random variable. It's just notation, really. It's nothing different from this concept here, but you will see in more advanced studies why this notation comes in very useful. When we study iterated expectation, this is going to be thinking of this as a random variable rather than just as a number is going to come in very, very useful. Okay, so just to recap again. So if you take any outcome in here, this needs to map you onto a real number. How does it find what real number it needs to map you onto? Well, it will look at what value the random variable x maps you onto. It will say, okay, given that value of x, I substitute in that value of x for a here, what is then the expected value of the random variable y, given that x is that value? Well, that will be a function of your x value. So here, we now have a function of s, which is going to be the expected value of y given x. So it's going to map every outcome onto this value. And that's also can be viewed as being a function of this random variable x, basically. So we could also draw in a line like that. And again, it's actually exactly the same function of this random variable x as is the random variable y. Okay, so we'll call it there for this video and continue our discussion in the next video.